Hi, class. So today I'm going to cover chapter 13.3. The title is Le Chatelier's Principle, and it has to do with what happens to an equilibrium reaction when you change it, when you disturb it. And we're going to talk about changing the concentrations of the reactants or products, or changing the pressure in a gaseous reaction, or changing the temperature of the reaction. So those are all the parameters we're going to change to this equilibrium, and we'll see what happens to the reaction when we do that. We're going to be using worksheet 12, so it'd be good if you have this printed out already so you can work through it as I go over it. And that's it. So let's get started. I'm going to share my screen and we'll look at this PowerPoint that I have set up. Oh, actually, you know what I'm going to do? I'm going to change to so you might see a picture of the worksheet up in the corner. So I think we're sharing my desktop. Let's look at this PowerPoint. So chapter 13.3, shifting equilibria. So in this, learning objectives will be to understand Le Chatelier's principle, and then be able to predict how an equilibrium system under stress will react. So stress is when you change the parameters for that equilibrium. And like I said previously, we're going to be changing the concentrations of the reactants or products or pressure of the system. There's a couple ways we can change the pressure or change the temperature. So basically this states what happens when the conditions of a reaction at equilibrium are changed, the forward and reverse reaction rates will no longer be equal. And we know that the reaction rate, we've learned this previously, depends on the concentration. And so if you increase the concentration of any component in an equilibrium, the reaction rate is going to be changed. And so when that happens, the system's not in equilibrium anymore. So Le Chatelier's principle states that when a stress is placed on a reaction at equilibrium, the system responds by changing the rate of the forward or reverse reaction in the direction that relieves that stress. Now, that seems a little, that's a little wordy. So I think it's a lot simpler. When we look at some examples, you'll understand what that statement means. When I read that, it doesn't seem very clear, but I think from the examples you'll understand it. It's not that hard to understand. One way you can understand, let's look at two tanks of water joined by a little tube. You can think of this maybe two reservoirs, you know, that are connected by a canal, or two lakes connected by a canal. Well, if a lot of snow runoff fills one of the lakes connected by a canal, you've disturbed the water level. So what's going to happen? The water level in this tank on the left is going to, lake on the left is going to flow over to the lake on the right until both lakes have the same water level again. So what we've done is we've added water to tank A. The water in tank A then responds by decreasing, and when that decreases, it adds water to tank B. So B doesn't remain the same. When A goes down, B has to go up, and they keep going until they reach equilibrium again. So I think this tank analogy pretty much explains, or is a visual, what might happen to an equilibrium reaction. If you add something to the reactant side, the reactant side is going to respond by making more product. Remember, when product is formed, reactant decreases. So here's a graphic. Here's a lecture, YouTube lecture I'm going to play for you. Might be a commercial at the beginning of this. Let's hope not. This is Professor Dave. There is a commercial. So let me skip that. I don't know how I skip that. God. Let's get out of that. Okay, there we go. Here's Professor Dave.
Chatellier's principle says that if you induce a stress on a system at equilibrium will shift so as to relieve that stress. Let's see some examples of a stress we can put on a system at equilibrium. First, we can modify the concentration of any compound. Let's say we add some of this reactant. That will unbalance the equilibrium, and the forward reaction will speed up to use up some of the additional reactants, turn them into products, and restore equilibrium. Equilibrium is said to have shifted right. If we add more products, it would shift left. Likewise, if we selectively remove one of the components, equilibrium will shift, use more of that solution for balance. That is one type of stress we could put on a system.
I'm going to add a note that so the equilibrium, when the system's in equilibrium, it's in balance. And so that's what that scale is kind of a good visual of if you add a reactant or a product, you're tipping it out of balance. And that's how it can restore balance.
Another stress is change in temperature. To see how this would affect the equilibrium, we have to see whether a given reaction is exothermic or endothermic. This tells us whether a reaction absorbs or releases energy and is signified by delta H, change in temperature. If delta H is negative, the reaction is exothermic and releases energy. So we can think of heat energy as a product of this reaction. If instead it's positive, that means it's endothermic and energy must be absorbed in the reaction. So we can think of heat energy as a reactant.
Okay, so I want to add something. So I said previously that the only thing that changes the equilibrium constant is temperature. So when you add heat, or if you heat a reaction up, that actually changes the equilibrium constant. But from this explanation of what heat does to the equilibrium, you can understand how it changes the equilibrium constant. So when we say the equilibrium is going to shift to the right or to the left, when you add heat, you're really not, you're going to increase either the amount of product or the amount of reactant. And remember, the equilibrium constant is the concentration of the product over the reactant. So when that happens, the equilibrium constant changes. Just remember that when heat is involved.
Once we translate thermodynamic data in this way, we can treat the word heat as just another substance involved in the reaction. Higher temperature means more heat, so things will shift to the other side and use up excess heat, stress. Cooling it down has the opposite. The third stress we can examine is changing the volume or pressure. Let's say the equilibrium involves gases. If we decrease the volume, to remember Boyle's law, we know that the pressure will go up. The smaller the volume, the more the particles will hit sides and exert pressure. If there is a discrepancy in the number of moles of particles on either side of the equilibrium, it will shift towards the side with fewer particles so as to alleviate some of the additional pressure. In this equilibrium between a diatomic molecule and two monoatomic molecules, the right side has twice as many particles. So shifting left means atoms fusing together, resulting in fewer particles, which lowers the pressure on the container. If we increase the volume, thereby lowering the pressure, equilibrium would shift towards the side with more particles in order to gain some of the lost pressure. Let's check comprehension.
All right, so that's it. Let me, get out of this. Let's go back to our PowerPoint. And another way you can think of Le Chatelier's principle is to remember the Q that we discussed previously. So you can think of, if we add reactant, remember that Q or K, let's remember K, let's write here. What? Let me see. I'm going to write something here. I'll write it over here in the bottom. So remember K is equal to, I'm going to do this on the product. I'll put a P for product over reactant. I think that's pretty good. I drew that with the mouse. And so this is what Q is equal to. So Q is equal to K when the product over the reactant is unchanging, the concentrations don't change. But if we add reactant, we're going to increase the denominator. That throws, this isn't equal to K anymore. In fact, if we increase the denominator, it's going to be a smaller number. So Q is going to be less than K. That's what that means. So if Q is less than K, what we have to do is we have to restore K. So that means decreasing the denominator and increasing the numerator. That means decreasing the reactant. If we've got reactant, we need to decrease it and increase the numerator, which means the product. So the reactant, so what's going to happen if you add reactant, you need to decrease the reactant and increase the product to restore the K. I hope that makes sense. If we remove product, then say if we remove product, then again, Q is less than K. So the equilibrium has to shift to the right to increase product. Let's see, next. If we, I'm going to erase my thing here, my image, because it's getting in the way. So we add product and look at this. We're going to increase this expression. So Q is going to be greater than K. And so we're going to have to decrease the product, which means the reaction is going to have to shift to the left to do that. I don't know. Okay, there we go. So there's all these. Come on. And lastly, if we remove reactant, then Q is going to be greater than K, so the equilibrium has to shift to the left to increase reactant and decrease product to restore the K. So consider the following reaction at equilibrium. We're going to add reactant. So if we add H2, we increase the H2 right here. Why is it not writing that? Oh, because it's an eraser. Okay, so we're going to increase H2. And when we do that, it's going to throw the equilibrium out of equilibrium. Q is going to be greater. Let's see, Q will be less than K then, because this is a reactant. So the equilibrium has to shift to product. So it's going to shift right. That's what the big blue arrow means. Now when it shifts right, because this has two reactants, H2 is going to be greater. After equilibrium is reestablished, H2 is going to be greater, but I2 has to go down. So for this reactant to shift right, H2 has to react with I2 to produce more hydrogen iodide. So this is going to go down. So we increase this. This has to go down. It's going to shift right, and this is going to go up. So that's how all the concentrations in this particular reaction will change if we added hydrogen. Now, since we had hydrogen, the hydrogen is going to be higher. So when equilibrium is reestablished, hydrogen will be higher, iodine will be lower, and hydrogen iodide will be greater. We're going to get to practice all this on the worksheet. Consider the following reaction. We're going to remove hydrogen. So if we remove hydrogen, we're making the denominator in our equation, the product over reactants, less. So Q is going to be greater than K. So we're going to have to, so this equilibrium then is going to shift to the left. If Q is greater than K, that means we have to reduce the product. So it's going to shift to the left. So we take this away. So we're removing a little bit of this. So we have to restore it. So the reaction has to shift left, which means HI has to go down. And I2 is going to go up. So I2 is going to get a little higher. So what's going to happen in the end? H2 will be a little bit lower because we removed some. But I2 is going to be a little higher. That's going to, and HI is going to go down. That's going to help restore the equilibrium. All right. Let's look at a change in volume of gas mixture. So what does change in volume do? So that was in the video. If you change volume, if you increase the volume, the pressure is going to go down. This has to do with Boyle's law. If you decrease the volume, the pressure is going to go up. And that's going to affect the side of the reaction that has the more moles, or the more molecules in the expression. So if you look at the left side here, we have 3 moles of gas here. So we have 3 moles of gas. And on the left, or on the right side, on the product side, we have 2 moles of gas. So that's what you have to look at when we're looking at changing the volume of the pressure. So if we increase the volume, that means the pressure is going to decrease. And so the greatest effect is going to be on the side where it has the greatest number of moles. So it's like decreasing this side. So if we decrease this side, the system is going to have to shift. We can move this. No, can't move it. In the direction to restore that. So if we decrease the pressure or increase the volume, we're going to decrease the pressure. The greatest effect is going to be in this side. So we're going to have to restore some of those molecules. So the system will shift to the left in this case. So increasing the volume decreases the pressure and the concentration of the gases, and the system shifts in the direction of the larger number of moles of gas. Okay, so increasing the volume makes this system shift to the left, restore the pressure. If you do the opposite, suppose, maybe that's on the next slide. Let's see, is that the next slide? Oh, yeah, shift left. Okay, so if we did the opposite, instead of increasing the volume, if we decrease the volume, that means increase the pressure. And that's going to, again, increase this side more than that side. So the equilibrium will shift to the right. So when you get a problem like this, the description is going to be either, or the stress that's going to be put on is either from the change in the volume or the change in the pressure, but it's really the same. If you increase the pressure, if you decrease the volume, that's going to increase the pressure. If you increase the pressure, it may come from a decrease in the volume. Not necessarily, you could be adding a gas. So increasing the pressure is like adding more gas to one side or the other. So here's the problem. Let's see, decreasing the temperature of an endothermic reaction. Decreasing the temperature of an endothermic reaction. Let me see. So here's an endothermic reaction. So since it's endothermic, the heat component would be added to the reactant side. So that's what's shown here. And remember, if you're giving the enthalpy, the delta H would be positive for an endothermic reaction. I might write up, oops. Delta, it's not a very good delta. Delta H is positive for an endothermic reaction. And you would add the heat over on the reactant side. Okay, it causes the system to respond by shifting the reaction towards more heat. We're decreasing the temperature. So we're going to take away the heat. That means the reaction is going to shift to produce more heat. It's going to shift to the left. So this would be a case where in an endothermic reaction, if you change the temperature of the equilibrium to a lower temperature, it's going to shift towards reactants to produce more reactants. So that means the reactant is going to go up, product is going to go down. That means the K is going to get less. So an endothermic reaction, if you reduce the heat, the K is going to decrease. Shifts the reaction toward the reactants. In an endothermic reaction, again, heat is on this side. If you increase the temperature, the reaction is going to shift the other way, away from the heat, which means you're going to form more product. And so the K is going to increase. The effect of temperature change on an exothermic reaction. So in this case, we're going to decrease the temperature. Now an exothermic is here. The delta H is going to be negative. So usually that's what you'll see. It'll give you a reaction. It'll tell you what the delta H is. If it's negative, it means the reaction's exothermic. Remember that from the previous chemistry course. And if it's positive, it means it's endothermic. So that's going to cause the reaction. We're going to decrease the temperature, which means we're taking away temperature on the product side. So the reaction is going to adjust by producing more product, which means K, the equilibrium constant, is going to increase. It's the only time the equilibrium constant changes is when you're changing the temperature of the equilibrium. The opposite is true if you decrease the temperature, excuse me, if you increase the temperature on an exothermic reaction, the reaction will shift to the left, increasing reactant and decreasing the K. The effect of a catalyst. So a catalyst, we learned previously in our kinetic chapter, was that catalysts speed up a reaction, but they don't really change the energies of the reactants of the product. So if we look at a reaction profile, so here's the reactants over here, here's the products here. All a catalyst does is lower the activation energy. Remember that, it lowers the activation energy. And so the amount of reactant over the amount of product in the equilibrium reaction depends on the energies of those two, of the energy of the reactant compared to the energy of the product. Remember, if the energy of the product is lower, as shown in this case, that indicates an exothermic reaction. So when the reactants form product, this gap right here determines whether it's exothermic or endothermic. So in this case, it looks like, I don't know, it's maybe 300. It's minus 300. So the delta H would be something like minus 300, which means it's an exothermic. All right, so that's it. I'll stop the screen share. And we're going to switch to the worksheet. So let's look at this worksheet on Chatlier's principle. We're going to go through this pretty fast. It doesn't take very long. For each of, there are no calculations. It's qualitative, and then understanding what happens to the concentrations of the reactants and the products. when you disturb the equilibrium. So for each of the following changes to the equilibrium, predict whether the forward or the reverse reaction must proceed to reestablish equilibrium. And so we have nitrogen monoxide plus hydrogen producing nitrogen and water in this first reaction. So the first thing we're going to do to disturb it is we're going to add hydrogen. So I'll zoom in here. So we're going to add hydrogen. And if we add hydrogen, hydrogen's a reactant. And so to compensate, we have to shift this right. So it's going to shift right. Shift right. Now there could be a lot more, that's all this question asks, but there could be lots of other questions asked. We could say, what does it do to the equilibrium constant? Well, is the equilibrium constant going to change? In this case, no, because we haven't changed the temperature. So the equilibrium constant remains the same. So for the equilibrium constant to remain the same, we're going to have to increase nitrogen, increase water. For it to shift right, the added H2 has to react with NO. So NO is going to go down. So in this case, the NO is going to decrease. The H2, because we added it after equilibrium is established, is going to be greater. This is an equilibrium with N2. So because it shifts to the right, N2 is going to increase, and H2O is also going to increase. Okay, so that's about all you can say about that reaction when we add H2. And the second one, we're going to add N2. Well, N2 is a product. So I'm not going to go through all this analysis, but I want you to think of that when you're going through these problems. And I'm just going to answer, it says predict whether the forward or the reverse reaction must proceed to reestablish equilibrium. So when we add N2, it's going to be the reverse reaction. We'll speed up. And that means it's going to go to the left. So sometimes we just put arrows to say which way it's going to shift. We're going to remove H2. So that means we're losing some product. So we're going to have to restore the product. So it's going to have to shift forward or to the right. Next, we're going to remove NO, which is a reactant. So it's going to have to restore reactant. So it's going to have to go to the left, which is called the reverse reaction. And that's how we'd answer that next one, number 4. Next question. Let me zoom out here and find the next question. Where's the next question? Oh, there it is, right there. There it is. Okay, let's zoom in. Determine the value of K. Determine if the value of K changes or whether the forward or reverse reaction must proceed to reestablish equilibrium. I think this should say or. So this is a different reaction. It includes nitrogen dioxide this time, plus oxygen and chlorine dioxide, changing in NO2ClO4 plus oxygen. So this is a delta H of negative 421.86. And I hope you know that that means it's exothermic. And so we'd put the heat. So we want to add, we can add heat over here. So we're going to add a heat component on the product side. So first of all, we're going to decrease the pressure by increasing the volume. We talked about that. So we have to count the number of moles on the reactant and product side. So first of all of the compounds or chemicals in the equilibrium expression are gases. So the NO2ClO4 is a solid. Remember, that doesn't occur in the equilibrium expression. So everything's everything in the equilibrium expression is a gas. So changing the pressure is going to affect it. If there was a liquid in there or an aqueous, or if there was an aqueous substance in there, then we can't say what's going to happen when we change the pressure. Okay, so changing the pressure and volume, we're only going to be looking at systems that only contain gases in the equilibrium expression. So on the left side, we have 1 plus 2 is 3 plus 1. We have 4 moles of gas over here. So 4 moles of gas, I'll write that. And on the product side, we have 2 moles of gas. And so when changes occur, it's going to affect the side with the most gas moles. So if we decrease the pressure by increasing the volume, that means we're going to have the greatest effect on this side. And so the reaction is going to have to go to the left. It's going to shift this way. And that would be the reverse reaction. So sometimes we'll say the reverse reaction is going to speed up to restore reactant. Or the reaction is shifting left. So there's a couple of ways we can express that. Next, we're going to increase the pressure of the system by adding helium. Oh, that's interesting. So we're adding an inner gas. It's not part of it, but we're increasing the pressure. So when you increase the pressure, that's going to affect the side with the most molecules. And so reaction would shift to the right to decrease the pressure. But would that decrease the pressure by adding helium? I think by adding helium, we're not really, that's an inert gas, so it's not really affecting it. So I think this might be no change. Because we're not effectively increasing the pressure of any of the reactants or the products. The last question is conducting the reaction at higher temperature. So if we look at where the heat component comes in, if we increase the temperature, the heat is on the product side, so it's going to have to increase the reverse reaction to restore equilibrium. It's going to have to shift to the left away from the heat. Is that going to affect the K? Yes, it is in this case, because the products are going to increase and the reactants will increase, the products will decrease. So K will decrease. Remember, K is product over reactant. So if it shifts to the left, we increase reactant, which is going to decrease the value of K. All right, let's look at the next one. I'm going to do one more. And these are all similar. They ask a few more questions about the equilibrium. And so just a few boxes to fill out here in this one. So here we have a reaction N2O4 going to 2NO2, and that's a familiar looking reaction. We've seen that one before, this equilibrium. So we're going to add N2O4 to the system. If we add N2O4, we're adding reactant that means we have to compensate in this equilibrium to lower reactant, so it's going to shift to the right. So right here, the first thing I do is we see what the disturbance is. Then I decide if it's going to shift to the right or left. So we say it's going to shift to the right. That would also be called the forward reaction. Is it shifting to reactants or products? Well, it's shifting to products. I'll just put a P for products. And what happens to the N2O4? Well, we said we increased N2O4, so that doesn't go back down to its original value. So it's, after equilibrium is reestablished, it's going to be a little higher. And NO2 is also going to be higher. All right. So if NO2 is increased, it's going to shift to the left towards reactant. NO2 is going to be higher, and N2O4 is going to be higher. Shifts to the left, we're going to increase that. This goes up, then it comes back a little bit. So you might think the initial change is if I do it in this box, the initial change is a big arrow, and then it compensates by shifting to the left, so it comes back down a little bit. But overall, it's going to be increased from where it was originally. So we're going to increase temperature. Look at the delta H. The delta H is positive. So we have to add our heat over on the endothermic side. So if we increase the temperature, it means we're disturbing the reactant side. So it's going to shift right. It's going to form more product. NO2 is going to increase, and N2O4 is going to decrease. And that's going to change your equilibrium constant. N2O4 is decreased. So again, it's going to shift left. N2O4 is going to be decreased. NO2 is going to be decreased. This shift to reactants. I'll let you fill in the next two on that one, and also the bottom. It's a similar exercise. I think you can do both of those. In the third page, there's a little note here. It says adding solids or liquids and removing solids or liquids does not shift the equilibrium. This is because you cannot change the concentration of a pure solid or liquid. There's only the concentration change that will change the number of collisions and hence shift the equilibrium. So in this case, we have calcium carbonate solid going to calcium oxide solid and CO2 gas. And so we're going to add calcium carbonate. So there's really no change because that's a solid. Calcium oxide, we're going to add that. There's not going to be any change. CO2 is added. So this is equilibrium. So we'll shift left. So if we add CO2, some of the CO2 is going to react with calcium oxide to reproduce that. So it's going to go down a little bit. If we decrease the temperature, again, it's endothermic, so that's going to have an effect. If we add a catalyst, no effect. The CO2 is decreased. If we take some CO2 away, well, to restore equilibrium, we're going to have to make more of it. Remember the K? Let me write the K. The K is equal to the concentration of CO2. That's all there is. So K is a constant value. So let's go back to problem C. If we increase CO2, it's not equal to K anymore. So we're going to have to decrease it to reestablish K. Let's go down to F. We're going to decrease CO2. It's not equal to K anymore. So we're going to have to increase it. So it's going to shift to the right. So the equilibrium still occurs if we change the concentration of CO2, but the concentration of CO3 and CaO doesn't change because they're solids. And lastly, I'll let you figure these out. Number 7, if you have questions about these, be sure to shoot me a note or an email or join me at office hours on Monday to discuss these if you don't quite understand any of them. So that's the end of Chatelier's principle, chapter 13.3. So the next lecture will be on 13.4, which that's a problem solving chapter. So take care. See you then.